Okay, so our new unit is water resources. Note the date of our next test. Not tomorrow.
22 to 29.
It's the final exam. Your final exam will be your water unit test. Remember, all the tests are cumulative anyways. The only thing different from the population test that you just took is that you will have the multiple choice and the FRQ on the same day. We might have 1 or 2 FRQs as we go through the unit on Mondays, but your next actual test is on the final exam weekend. Water resources is the unit that we're going to finish out the semester with. And as we get started, we need to look and see where water is going to come from later.
Unlike every other planet in our solar system, Earth's surface is 70% liquid water, which, while useful for life, is also kind of weird, because everything we know about how and when our planet formed says Earth's surface should be bone dry. The story goes like this. Our solar system formed from the collapse of a large cloud of dust and gas. The dense blob of gas at the center ignited to form the sun, which, as a young, unstable star, unleashed a fierce solar wind. Over time, this stream of charged particles pushed the remaining gas cloud farther and farther out, leaving only solid particles behind to clump together into rocks, planetesimals, and finally, the rocky planets of the inner solar system that we know today. And here's the problem. Water, in the form of ice, couldn't have been one of the solid particles that stuck around to form our planet, because the early inner solar system was far too hot for frozen water, and any water vapor would have been blasted away by the solar wind. So if Earth didn't start off with water, how did we end up with such splendid oceans? We know H2O wasn't manufactured here over the eons, because natural processes like combustion, breathing, and photosynthesis create and destroy roughly equal amounts of water. And either way, the amounts in question are so minuscule that they can't account for the abundance of water on the planet. Since Earth's water was neither part of the original package nor manufactured here, it must have flown in from far away, on meteoroids or comets or other bodies originating in the outer solar system where they were far enough from the sun for frozen water to survive. The dirty ice balls we call comets are a logical candidate for the source of our water, but were ruled out when we discovered that they were far richer in heavy hydrogen than Earth water. Heavy hydrogen has a neutron as well as a proton in its nucleus, and for every million hydrogen atoms in Earth water, about 150 are heavy ones, while typical comet water has twice that many. These mismatched chemical signatures suggest that Earth's water couldn't have arrived on comets. It turns out that the most likely source for Earth's water is a type of meteorite called a carbonaceous chondrite. Chondrite is just the name given to the class of stony meteoroids that most commonly strike the Earth. But only the carbonaceous chondrites contain water, as well as lots of carbon if you couldn't tell from their name. They have water in them because they formed out beyond the sun's frost line, and what's more, their water has levels of heavy hydrogen similar to that of Earth water, strongly suggesting that these Earth crashers are the source of our ice caps, clouds, rivers, and oceans. And thus the water that turned our planet into a blue marble came quite literally out of the blue. This episode of Minute Earth is supported in part by Tab for a Cause, one of our subscribers.
All right, so that's where water originated from. Water is important. We are a very water-intensive animal. We need it to survive, so we have to drink it in. We need it to grow our crops. We need it to have the animals that we're going to eat eventually. And almost all of our manufacturing is heavy in water. We know that approximately 70% of our Earth is covered in water. That's why it's the blue planet. But very little of that is water that we can use. Very little of it is fresh. 2.6% of the water on the planet is fresh water. We can't use the salt water. We don't have the right organs to maintain our water concentration, our osmoregulation, like fish do. So we need the fresh stuff, and there's very little of it. 68.7% of the fresh water on the planet is frozen, which means it's in the ice caps, it's in our glaciers. Some countries like Saudi Arabia have come up with crazy ideas that they can take a boat and lasso an iceberg and drag it back to Saudi Arabia. Kind of works. The majority of that iceberg melts in transit. It's also really fossil fuel intensive and very expensive, so they're not going to do that regularly. 30% of our fresh water is groundwater, which means it's located under the ground, under the land that we're standing on. We can access this fresh water using wells, and if you live in the Midwest, East Coast, chances are that the water that's coming out of your faucet is from your own personal well on your property. There's good things and bad things with that. You're not paying a water bill because you're pumping that water up yourself. The bad thing with it is that there's no regulation of that water. No one is checking how safe that water is. And we're going to watch a video later in the unit that's going to show in Texas, the people didn't know that the water that they were pumping up from their wells contained chemicals from a nearby plant. Those chemicals were causing cancer. And so they started like looking around and go, wow, why do all of my neighbors have cancer? Because of the water that they were drinking. So we do have ways to access the groundwater, but you know, 0.3% is surface water. What would I consider surface water? Lakes and rivers. So surface water is anywhere that you could go and take your hydro flask and dip it in and get a drink. I don't recommend it because everything that ends up on the ground ends up in the surface water. So your dog poops, it rains, some of that poop's gonna wash out into a river. But technically you could drink it. 97% of the water on Earth is salt water. We cannot utilize salt water. We have ways of getting rid of the salt, of desalination. Good. We have ways of getting rid of the salt. It's very fossil fuel intensive and very expensive. So it's kind of like a last resort. If we run out of every other source, if we can't get water any other way, then we'll resort to desalination. Your atmosphere contains only 0.001% of all the water on the planet. It's really important though, which we're going to see in a minute. You guys need to know these numbers. They show up on tests all the time. So your atmospheric water, very small percent, 0.001%. However, this 0.001% is going to kind of drive your climate. It's going to determine what you can grow, where you can live. It's essential to the global water distribution. So the majority of our atmospheric water evaporates from the oceans. When it evaporates as pure water, only H2O. So the salt and all of the pollutants stay in the ocean, just the water goes up. That water then gets blown around the globe by the wind currents, condenses if it gets cold enough, and then rains or snows, dropping it out of the atmosphere onto the land. Is that global distribution of water equal? Does everyone get the same amount? No. Here in Southern California, we get very little of it. If you end up going to school in Oregon, they get a ton. So it's an unequal distribution. This unequal distribution of that atmospheric water leads to conflict because we all need it. Precipitation directly affects soil fertility. Obviously, you need rain in order to grow crops. Continued drought leads to topsoil loss. It's a snowball effect. So if we have continued drought, the plants start to die. If the plants die, their roots are no longer holding the soil. When the wind blows, the topsoil moves away. If we lose the topsoil, we lose the fertility of that land. It makes it harder to grow plants without adding nutrients. In areas that are prone to drought, like Southern California, we typically do not have the infrastructure to store water, which means when it rains, our infrastructure is designed to get the water away from our cities, away from our homes as fast as possible. That's why all of our major rivers are concrete basins, so that you increase the flow out to the ocean. We do that to prevent flooding in our cities. The downside of that, though, is all of this precious water that's falling on our desert community, we're sending out to the ocean. We need to come up with catchments. And there is a movement, now that we've had some extended drought, to do things like these rain barrels, where you get a gutter system on your house. Not a lot of our houses have gutter systems. They're common Midwest, East Coast. But what it is basically a pipe that runs along the edge of your roof line, and all the water that falls onto your roof, instead of like being a waterfall in front of your front door, gets diverted off to the sides. We can put a rain barrel at the bottom of that gutter system to collect all of that water. What can we use that water for? Watering the plants and the grass. If you guys look at our hillsides, is the natural color of Southern California green? No. But everywhere that we have humans living, we've got these beautiful trees and all of this grass. Well, it takes a lot of water. So we could capture water like this and use it to irrigate. What else could I use this water for? It's dirty, it's off my roof, so I'm not gonna shower with it, I'm not gonna drink it. Could I flush my toilets with it though? Yeah. So water that's gonna go into the sewer system anyways. A flash flood occurs when the water can't percolate or infiltrate, i.e. soak into the ground. In ideal conditions, all of the water that falls hits the ground and either ends up in surface water, like a lake that maybe we could draw from later, or it's going to end up in groundwater, so it soaks through the dirt. In areas that are prone to drought, they are also prone to flash flood because the longer you have drought, the longer the soil goes without water, the harder it cements. And any water that then hits it runs right off of it. Also in our area, we tend to have clay as one of our main components of our soil, and you're going to see in a later unit that clay doesn't allow water to go through. We've also, in cities like Las Vegas, cemented over the dirt. So there's a lot of roadways and concrete jungles. Well, water's not going to soak through that either. All of this leads to flash floods. You are not going to die of drowning generally in a flash flood. Okay, who's been to Zion National Park? Anyone? My favorite place. Zion's my happy place. The main draw to Zion, it's in southern Utah, is that you go into what's called the Narrows. So it's a big kind of canyon, and the Narrows are a slot canyon. So you go down a couple of steps and you actually hike through the water. So you're ankle deep to knee deep in the water almost the entire time, and you can hike back there for miles. There are places in the Narrows where it's narrow. You can put your arms out to either side and touch cliff, and that wall goes 600 feet up from where you're standing. It's never really deep enough that you have to swim through it. But it is prone to flash flooding because it's in a desert area without a lot of infiltration when it rains. I'm going to fast forward a little bit of it because the guy's kind of a dork. This is the entrance into the Narrows, so you are on a paved path for about a mile, and then you go down 3 or 4 steps, and you're actually in the river. And note, it's only ankle deep. So this is where you enter the hiking point. Now I will say this guy's doing something very wrong here, and so are everyone else who's in the Narrows at this point. When they panned the camera up to show the beautiful red cliffs, did you notice it was raining? Usually you don't want to go into a river when it's raining, especially not a slot canyon, but it doesn't only happen when it's raining in the park. I've been at Zion when it's 110 degrees in August and the sun's shining, and there's been a flash flood because it's rained 30 miles away, and they have the monsoonal flow, so they have like the big thunderstorms come through. The water is relatively clear. That's a sign that things are good. The precursor to a flash flood and how the people knew to warn them to get out is the water will start turning muddy, like minutes before the flash flood occurs.
This is the Narrows at Zion National Canyon.
This is the same point that he just walked across. It's not the depth of the water that's going to kill you. What's going to kill you? The debris. So as this is coming down, the current has increased, so it's probably going to knock you off your feet. And then anything that was on the banks of this river is now in the river. Look at the size of these trees.
It flooded right before we got there. And we just ran out of the water. Might still be dangerous. Where are they? Yeah, the guys, there's 2 guys in front of us who warned us. I think they're probably on the edge, hopefully. We don't see them running down here.
So it's not the depth, it's all of the debris. The flash flood like this, the one I saw a couple of years ago, it lasted all of 30 minutes and then it was back to a normal water level. So you could, if you could get up on the banks, kind of wait it out, but sometimes you have to be pretty far up. About 2 or 3 years ago, there was a group of tourists that were top to bottom hiking, so you can enter at the very top of it and hike all the way down. Usually you camp one night in the canyon. About 5 of them drowned because they were knocked off their feet, knocked unconscious, and then drowned in very shallow water. It's not just in rivers, by the way. It could be in dry riverbeds as well. We've had a lot of fires in Southern California lately. The fires take away the vegetation. The vegetation is no longer holding the soil in place. And when you get rain, you get flash floods. And that's what they're worried about with every storm that's coming through now. That's why we are getting weather alerts on our phones, even if we're only going to get half an inch of rain, because of the fires that have been in the area. Here is a flash flood in 2018 in Utah. Dry riverbed, and all of a sudden it's a mass of mud and trees.
Oh, wow. Wow.
Again, not the amount of water that's going to kill you. Wow. We've talked about the Dust Bowl before. This was in the Plains States, Oklahoma, where we took grassland and we said, wow, if native grasses are growing here, we can plow over this and plant wheat and corn and oat, which are grasses. They're just more water intensive than the grasses that were originally growing in Oklahoma. And so we had some really poor farming techniques in an area that wasn't really designed to have intensive farming, and then they had a drought. This resulted in them losing the topsoil when the wind blew, and we ended up with the Dust Bowl. There's a video on there. I've shown you videos of the Dust Bowl before. It's essentially just walls of dirt that are coming across. If you've ever been out in the desert during a sandstorm, it's the same thing. You put your hand in front of your face and you can't see it. This was an extended 10-year period where this was going on. Unfortunately, you guys no longer read Grapes of Wrath by Steinbeck. Awesome book about the Dust Bowl, about farmers that lost their farm there and ended up coming west to California to pick grapes because they couldn't have a life in this area anymore doing what they traditionally did. If your great-grandparents are still around and were alive during this time, it'd be interesting to talk to them about their experiences during the Great Depression and the Dust Bowl. Lakes are our major source of accessible fresh water. It's on the surface, it's there, we can get it. I want to put this up here though, this picture of the Great Lakes, because a lot of you all are California kids, which means your idea of the lake is standing on the shore of Lake Arrowhead or Big Bear Lake and seeing the shore across the lake from you, right? That is not a lake. My mom's family is from this area on Lake Michigan. You stand at the beach on Lake Michigan, you can't see across Lake Michigan. There are waves big enough to surf on Lake Michigan. Big container ships with like the containers that you see on the trains get sunk in these lakes. This is what a lake looks like. That's when we say major source of fresh water. We could very easily in a year drain Arrowhead if we start using it for drinking water. We can't do that to the big lakes. The majority of the world have lakes that look like this, not our little puny Southern California lakes. We've talked about how lakes are classified before. Oligotrophic is no nutrients and therefore no life. Mesotrophic is the middle ground. Meso means middle. You have enough nutrients to have a lot of primary productivity, a lot of life, but not enough that you end up eutrophic, which is the last category, where you have too many nutrients and things start dying off. Residence time refers to how long a single molecule of water is going to be in any store or reservoir. So remember those system diagrams that you drew where the store is the box? Residence time is how long is a single molecule of water going to be in that box. If we're talking oceans, when you dip your toe in, that molecule of water could have been in that ocean for 37,000 years. Think back to history. What was going on in the world 37,000 years ago? That's the water molecule that's there. Ice caps are about 16,000 years. Our groundwater is 300 years. That's important because in California, we've kind of messed with our groundwater. As in, we were in about an 8-year drought, and we weren't going to decrease our agriculture because it's the main source of income for our state. And so we pulled from the groundwater using wells. We pulled so much groundwater that the elevation of the Central California actually dropped because we took the water. Wells that used to only have to be 300 feet deep are now having to go 1,000 feet deep to touch water. This is not a great thing because our aquifers and our wells have really long residence times, which means we're not going to be able to replace that water with any speed, even if we do have a lot of years of good rain. Aquifers are 10 to 20,000 years, and later this unit will talk exactly about what an aquifer is. Our rivers have short residence time, 12 to 20 days, which means if a molecule of water ends up in a river, in 12 to 20 days it will end up in a lake or in the ocean. And then our atmosphere is very short, 9 days. It evaporates out of the ocean, is in the atmosphere for 9 days before it ends up somewhere cold enough that it's going to condense and either fall back to Earth as rain or snow. So is it a renewable resource? It depends on where it is and what its residence time is. Our atmosphere and our rivers have very short residence times. So they renew very quickly. They refresh. They're constantly new. Groundwater and aquifers are kind of the middle. And our oceans and our ice caps have very long residence times. They are considered non-renewable. When the glaciers go away, they go away until the next ice age. And who knows when that will be. You guys have seen this, you've drawn it, you've done the system diagram. Remember in the system diagram, our stores are boxes, and the size of the box is relative to how big that store is, how much it contains. Our transformations are going from one form to another, so evapotranspiration is going from liquid to atmosphere. And then our transfers, it stays as water or as a gas, it just moves from one store to another. All of this comes down today to human impact. How are we utilizing our water resources? Remember, we are water intensive. So we're using it for irrigation for our crops, for feeding our animals, for manufacturing our clothes that we're wearing, and the paper and the computers and all of that. We also then discharge into our bodies of water. So you take a shower, and all of that soap that you showered with, all of the dirt and crud that was on you, ends up in the pipes. Now, thankfully, in our country, that ends up in a sewer system and it's cleaned before it's discharged into the rivers and lakes. But there are countries where it goes directly into the river or lake with all of that soap and all of that crud. That could pollute that body of water, making it unusable. We also tend to manipulate our rivers and our bodies of water. So in California, our main rivers, the Santa Ana, the LA, and the San Gabriel rivers, we've concreted. So what you're seeing on the bottom of the screen is the LA River. We've taken what used to look like, if you've ever hiked Oso Creek Trail, a beautiful wild river. and we've cemented the whole thing. And we did that so that the water will move more quickly out to the oceans and prevent flooding. If we want to build a freeway, we're going to move that river underground through a pipe. Or if I want to build my house, I can shift that river 5 feet to the left, 100 feet to the left by just manipulating the riverbank and using concrete and stuff. We've also diked and dammed our bodies of water. Anyone know the difference between a dike and a dam? A dike is salt water, a dam is fresh water. We do that to make our reservoirs and to make lakes. Here are your case studies. When I say case studies, this is what AP and IB requires you to know. So if you have to write an essay about the impact on a local or a body of water, here they are. We're going to give you 3. The first one's the Ariel Sea. It's located in what is formerly the USSR. It has no terminal outflow, and it was fed mostly by rivers coming in, and we started stealing from those rivers to do agriculture. And so the flow into the lake pretty much ceased. And in the last 5 years, it's gone down by 90%. So it's devastating to the people that used to fish that lake. It's devastating to the people that live on the shores. These videos are the information for the case study. So instead of me having you read an article, and we'll do some of those later, instead of you reading the article, I've got the video. So just like you would kind of mentally take notes on an article, you have to do that with the videos. No like sleeping, playing Candy Crush, that kind of thing.
The town of Aral was the epicenter of this region's once prosperous industry. It's hard to imagine, just 40 years ago, this was a bustling fishing port.
There was a beautiful sea with waves coming up to the beach. It was wonderful. There were no fish in the Soviet Union like the fish in Aral. We thought that gradually life would get better.
The rivers that fed the sea were diverted to irrigate plantations created during the Soviet era. Since the 1960s, over 90% of the sea has disappeared. The exposed seabed extends for hundreds of kilometers, leaving ships marooned in this newly created desert. Aid from the World Bank has been used by the government to build a dam at the sea's northernmost tip. The dam is now at full capacity, and although it hasn't brought the sea back to the town of Aral, it has helped other local communities.
By the late 90s, only 8 houses were left in this village out of 90 houses. But when they built the dam, it improved. People are coming from all over the place and fishing here.
Here in Aral, people are hopeful that one day the sea will come back to their town too and provide a future for their children.
Some people believe that the sea will return. Others insist that it will not. Maybe my grandchildren's grandchildren will see water here.
The disappearance of the Aral Sea was a tragedy for the local people, and one they are still coming to terms with. Rustam Qabil, BBC News.
Okay, our other example here is the Ganges Basin in India. Deforestation at the headwaters or the top of the river has made it so that the water can't infiltrate, it's not held, and when it rains, all of that water goes down the river. That then floods this entire basin, flooding out poor rural villages and the people that live there. These are your international case studies, but we do have a case study in our own backyard. So in eastern San Diego County, eastern San Diego County, let's see if I can talk today, kind of by Ocotillo Wells and Glamis if you ride dirt bikes, kind of out by Palm Springs in a way, is the Salton Sea. This is a body of water that was created entirely by accident. They were piping water from the Colorado River to LA, and there was an accident, and the Colorado burst its dam, and all of that water ended up in this low-lying spot in the desert. They then decided that, hey, here's a tourist spot, right? Palm Springs is already a tourist spot. Now we can have a body of water where you can water ski and hang out and enjoy the sun in the desert with a lake. Pretty cool. It was fed by irrigation water, which kind of makes us scratch our head now in 2020. But basically the farms in the area would flood their fields and all of the runoff would end up in the Salton Sea. With all of that runoff came all of the pesticides and the herbicides and anything else that was being sprayed on these farms. It was okay though, because it kind of precipitated out and ended up at the bottom of the lake or the sea. The problem is we've gotten smarter about our water usage. Our farmers are getting smarter about their water usage, and not as much water is going into the sea. There's no outflow because it's not a natural body of water. And so what water is there leaves the sea through evaporation. So the pure water leaves everything else there. As this lake is receding, all of those pesticides and herbicides are being exposed, and when the wind blows, it blows it into Riverside, into some of the poorest communities in our area. I'm going to show you the video right now, and it's talking about a couple proposed. One's a little wacky, but ways that we can solve the problem. Again, make sure you're paying attention to the video.
Every bit of that plant is full of mercury, arsenic, selenium. It's full of it.
The largest impact, of course, will be dust. The cost of not doing anything could be in the tens of billions of dollars.
We are screwed because 20 years ago, not enough people were thinking 20 years ahead.
Little by little, the Salton Sea is disappearing, or they don't want to leave their homes. 4 years into California's historic drought, communities all over the state are desperate for water. And what's happening here around the Salton Sea could be an alarming premonition of what's to come.
All right, so that's what's happening in your own backyard. So we have the case studies that are international, but it's not something that's like, oh, that's in a different country and we don't have to worry about it. That's an hour and a half southeast of us. Last thing we want to talk about today is the idea of currents. And again, we've talked about currents already. These are currents of water that are moving nutrients around. They're moving temperature around. And we have two types of currents. Surface currents, which are the first 400 meters of the ocean. These are driven by the wind and by the gravitational pull and deflected by the spin of the earth. What is that deflection called? Begins with a C. Coriolis effect. Hopefully that sounds somewhat familiar. Coriolis effect. Our deep water currents are thermohaline. They're driven by salt concentration and temperature. Less salty water and warm water tend to float on the surface. Cold, salty water tends to sink. Our ocean currents do moderate our coastal climates. That's why in the month of December, LA's got an average temperature of 68 degrees. Relatively moderate for a North American winter. El Nino is going to affect this by changing the pattern of our currents, which then changes the wind currents, which then changes our distribution of water around the planet. Long period on a Friday, but we're